So here's the coordinate ascent algorithm for doing map inference for the probabilistic matrix factorization model. What we have as an input is an incomplete ratings matrix M, where the measurements in M are indexed, the locations of the measurements are indexed by omega, and we also input a rank D that we want to learn. So we input the dimensionality of this latent space that we want to embed all of these users and objects into. The output is going to be N1 user locations, where each user is located in RD, and N2 object locations, where each object is also located in RD, so the same space. First, we're going to initialize each of the object locations. So we could have also initialized the user locations first and then flipped the algorithm. I've chosen in this slide to first initialize the object locations. For example, we could just generate them randomly. Then for each iteration, we follow the two coordinate ascent steps. First, within a particular iteration, we update each of the N1 user locations by maximizing the objective over each user location given the current values of all of the objects, all of the locations of all the objects. So we solve this equation, plugging in the current locations of the objects and using the data here. Then the second half of the same iteration will be to update the locations for all of the objects. And so for each value j, we update the location for object j, solving this equation where we use the relevant locations of the users. We use all of the users who have rated that object and also all of their ratings here. So we iterate back and forth between these two steps, and eventually the algorithm will converge. We can assess this convergence by calculating the log of the joint likelihood. That's the function we're trying to maximize, so we can evaluate that function after each iteration to see if it's converged or not. And then when it's converged, if we want to make a prediction for a particular user I and a particular object j that we don't have in the matrix M, we'll predict the corresponding element in M to be the dot product between user i's location and object j's location. And then we can round it to the closest rating option. And that's how we're going to be able to make a prediction for any user and any object that we don't know a rating for. We can pick out the user's location, we can pick out the object's location, and we just take their dot product, and then we round to the nearest legitimate possible rating. And that gives us our rating, our prediction of their rating. So we get some sort of embedding like this. This is a simplified example where we have the data living in R2. In practice, the data would most likely be in a higher dimensional space, like R10 or something like that. And for every movie, we have a location, and also for every user, we have a location. And so we can use this to visualize or to understand what's going on. For example, we can take a particular movie. This plot is not necessarily the best one to consider, but we can take a particular movie and we can say what are the 10 closest movies to this movie. And what we should see is that that list makes sense. So if you picked Star Wars, most likely the closest movie to Star Wars will be Empire Strikes Back, something like that. Now if we return to the original example that I showed, it's easy to understand why this latent space embedding of users and objects should end up being interpretable, where proximities between things will be meaningful. For example, if we look at the movies Caddyshack and Animal House, and we agree a priori that they're very similar and users should rate them similarly, whether they like them or not, we then have that this column is the column of the ratings that were given to the movie Caddyshack, and this is the column of ratings given to the movie Animal House across all of the users. So again, we only have some of the measurements in here and here. we've run the probabilistic matrix factorization algorithm to take this missing data matrix, this matrix with many missing values, and factorize it into a product of this matrix times this matrix, where the left matrix is n1 by d, and the ith row corresponds to the location for the ith user, and the right matrix is d by n2, where, for example, this column corresponds to the movie Caddyshack, so the jth column here corresponds to the jth column here, and this column corresponds to the location for Animal House. So if I want to know what this column is equal to, it's about equal to this times this, and similarly, this column is approximately this matrix times this column. Now, if we assume that these two movies should have similar rating patterns, so these two vectors should be very close to each other in a very high n1 dimensional space. What we're saying is that this vector is equal to this matrix times this small vector, and this vector is equal to the same exact matrix times this vector. So if these two columns look alike, if they are very close to each other, then that means that these two columns also have to be very close to each other, because if the values in these two columns differ significantly, then the product of this vector with this matrix will be very different from the product of this vector with this matrix. And so if these two columns are highly correlated, in the matrix factorization language, that means that these two much smaller vectors are should be very close to each other. And whatever error there is either due to the Gaussian likelihood, which absorbs a lot of the error, or it corresponds to the slight variation in the values in these two vectors. And so we can intuitively make this argument for any pair of movies, and also for any two users. If I pick two users and they have very similar ratings, then their corresponding rows of ratings will be equal to the corresponding rows of these vectors times the entire matrix here on the right. And again, those two users should be located very close to each other in that space. Therefore, if I want to, for example, pick two users, and I have one user viewed Caddyshack and loved it, but didn't view Animal House, and then another user viewed both movies and liked both of them a lot, and they also agree on many other movies, then those two users are going to be very similar to each other in this matrix. And then when you look at their dot products, that fact translates to the user who didn't rate one of the movies giving a similar rating to the movie as the other user who did rate the movies. So that's where this idea of collaborative filtering comes in, that users can kind of influence each other's ratings and give information about what other people will rate based on what they liked. Finally, I want to take an opportunity to connect the ideas we've been discussing in this lecture about matrix factorization to ridge regression, which we discussed quite a bit previously. And in that sense, we're going to see what I mentioned in a previous lecture, that the difference, the boundary between unsupervised and supervised learning algorithms is a little bit vague. And in this sense, we can almost view the collaborative filtering problem with using matrix factorization as kind of like a supervised learning algorithm, although not exactly. To see the relationship between matrix factorization and ridge regression, let's focus on the update for one specific movie. So in this case, we have the ratings matrix that's an incomplete matrix with a lot of missing values. We focus on one particular object, say the jth object, which corresponds to this column. If we only have these particular ratings for that object, that means we have points here where you see a black dot. Those are the points where we have ratings, and every other row has no data there. Then we can view the ratings that we have in these dimensions as being approximately equal to the corresponding rows of this matrix. So this row corresponds to this row, times this vector in the jth column. And now we can take this matrix factorization problem, restrict it to the jth object, and view this as a sub-problem like this, where we take the ratings that we have, make a smaller vector. So I've taken these values and put them in a smaller vector, and we're saying that those values are approximately equal to the corresponding rows of this matrix, which I now take out and put into this full matrix here, times this column, which I put here. And now when I update the location for object J, what I want to do is actually solve a miniature problem that looks like this. And so let's remember in the ridge regression setting what we did. What we did there was we minimized the sum of the squared errors of this approximation to this data vector. In that sense, you could also think of it like minimizing the sum of squared errors of the corresponding value mij in here minus the corresponding vector ui, which is the row here, times the vector vj. We summed those up, and then we added an L2 penalty in the ridge regression problem to the magnitude of vj. If we view this little miniature problem as a ridge regression problem, what we'll find is that we get this sort of an update as well. So this was actually the ridge regression update. This update for the vector vj corresponds to a ridge regression update. The equation is the same, where for any particular user I that rated object j, we're using the user's location as the covariate vector for that rating, and then mij corresponds to the output that we want to now predict for that particular rating. So in ridge regression, remember we actually had these outputs and we had the inputs as well. We wanted to predict an output based on the input covariate vector. In this case, those corresponding covariates are themselves unknown, and we want to learn them. So we can view the matrix factorization as a sequence of n1 plus n2 different ridge regression problems that we solve iteratively. We can also think of this as a least squares problem if we want to remove the Gaussian priors, in which case if we view this as a least squares problem, we have this update. All we do is remove this additional regularization term down here, and we get this sort of an update. And so that would correspond to doing maximum likelihood for this problem. So this sequence of updates for each column and each row corresponds to maximizing the likelihood of the observed values given u and given v, instead of maximizing the joint likelihood. However, notice that for this, in this case, if we did not put priors on u and v and simply did maximum likelihood, in order to invert this matrix, we would require that every single user has rated at least d different objects, and similarly we would require that every single object has been rated by at least d different users in order for us to guarantee that this inverse can be done. So for this problem, it's most likely that that's not the case, that we have that every user has rated more than d objects and every object has been rated more than d times, especially if a user is new or an object is new. And so we can kind of see here where the Bayesian approach is actually necessary for this model. Previously, it wasn't necessary, it wasn't required in order to make progress. For this type of a model, we need the additional regularization represented by this additional matrix here, which corresponds to a Gaussian prior, in order to make sure that we can actually invert this matrix for every single user, and therefore that the algorithm won't crash because we have a non-invertible matrix.